Well, good afternoon and welcome to the late session on Ceph. Before we begin, just to sample the audience, how many of you use Ceph in production today? Wow, awesome. How about, again, we have sort of a question that's somewhere between, sarcasm and reality. So, how many of you actually run databases on Ceph today in production? Okay, so I guess our question is valid to some degree. How many of you have actually tried it, but decided not to do it? Okay, all right. So I guess we'll get to your pain points. Once hopefully we'll answer some, and otherwise we'll try to get some details during the Q&A. So my name is Tushar Guhad. I work for Intel. I'm one of the technical leads there. I run most of the Ceph activities at Intel. We also have Paul Dardo here from Dell. So Paul, why don't you go ahead and introduce yourself?
Hi, I'm a senior principal software engineer at Dell EMC, and my area of focus is Ceph. So a lot of what that means is essentially coming up with architectures, helping size hardware for customer engagements, Ceph benchmarking, and that sort of thing.
Great. So this is the standard slide that I've always used, for most of my OpenStack or other conference presentations. But again, for this audience, Ceph does not need an introduction. It's just at a very high level, most popular block storage for OpenStack. That's why we're talking about it at this venue. It's been around for more than 13 years now, has a vibrant community behind it, commercial support options, and some features that make it very attractive for database installs, like the self-healing capabilities, no single point of failure. And calling out the latest user survey, Ceph remains right about 60-ish% of the OpenStack deployments for the storage backend of choice. So databases has been that elusive workload that we've been talking about for a while on Ceph. When we talk about databases, all flash backends come to mind. So that's what I mean here by NVM, non-volatile memory. So when we look at a workload characterization of the high performance block versus warm block versus object, the focus of today's talk is mainly around the top category there, which is basically the high performance mid-tier, medium-sized installs for Ceph. So 2 years ago or so is when we started talking about databases on Ceph at various events, including Red Hat Summit and Percona and so on. So this is kind of a long overdue an update that we're doing here today. So talking about databases, there are many SQL options that we could talk about. So we've been working closely with Dell on Postgres as one of the workloads, which hasn't been covered in the past. So we chose to talk about it today. This slide shows the various deployment models with which you can integrate Postgres on top of Ceph. So what's shown at the bottom is basically a all-flash Ceph cluster, whereas the top shows the various deployment models, including bare metal, containers, and virtual machines. So in this particular case, our install used a bare metal instance of Postgres with kernel RBD backend. So as you guys know, kernel RBD and librd are the two alternatives, and so we have experimented with both backends, but we basically are presenting today just the kernel RBD backend for those bare metal installs. So So I'll come back and talk to you guys after after the PostgreSQL treatment from Paul about more things we are doing. But for now I'll hand it over to Paul to go through the details. So.
Thank you. Okay, so one of the things that we did at Dell as part of refreshing some of our ready architectures is to, and this is from the block storage perspective, is to essentially think about what are the different categories that we want to address? How do we want to segment the architectures that we come up with? How do we want to define it? And what we came up with essentially is two. So the first one is really for customers who need the very top performing Ceph clusters that they can get, right? And then the next one is, well, not everyone wants to pay that price. Some people may have more modest requirements. They may require more storage capacity. So this next one is what we refer to as our cost optimized block storage configuration. So that's the one that we're going to be talking about today. But we are working on a higher performance all NVMe ready architecture as well. Okay, so let's talk a little bit about what does this cluster look like? What are the components that we're using? So in the array that we set up, we have, it's 25 gigabit Ethernet. We have 2 Dell S5248 switches, 48 port switches. We have an admin node, so it's a 1U R640 for Ceph Ansible deployments, for monitoring purposes and so on. There's no real special hardware requirements on that particular one, so it's just kind of a garden variety R640. For our Ceph storage nodes, we chose the R740XD, and we're using dual Xeon Gold 6152s, which is kind of at the higher end of the Gold spectrum. So this is 22 cores, 192 gigabytes of RAM. We're using the HBA JBOD controller and the BOS card for handling the OS. We've got a pair of 25 gigabit NICs. This is in a 2.5-inch drive chassis form factor with 24 front drive bays. And as far as the storage devices go, we have 16 SATA SSDs for our data, for our OSDs. And then we have 4 P4600 NVMe devices for our BlueStore, Wall, and RocksDB. So a couple of points that I'd like to draw your attention to here is the first one is that you do not notice separate nodes for Ceph Monitor. And the idea behind that is that we wanted to leverage some of the more recent enablements of being able to run Ceph daemons containerized and co-located. So that's what we're doing here. And that's the reason why you don't see 3 additional nodes for Ceph Mon purposes. The other thing that I'd like to call your attention to is this is a 4 Ceph storage nodes. And this is what we would refer to or kind of think of as a starter configuration. So why 4 nodes? Well, 4 nodes is kind of a nice size for setting up a POC environment. I would say it's kind of an entry-level size for standing up a production cluster. In that case, you might want to consider 5 nodes. But the idea is that even though we're talking about 4 nodes as a starting point, this architecture is scalable and can go up to multiple racks. So the point that we're starting with 4 nodes doesn't mean that we're limited to 4 nodes, or even that we're suggesting that you would use 4 nodes, right? Okay, so from a software configuration standpoint, we're running RHEL 7.6 with Red Hat's Ceph 3.2, Luminous-based, BlueStore OSDs. I mentioned that we're doing containerized and co-located daemons. We have 16 OSDs per node, so a total of 64. We have a 4-to-1 ratio of data drives to NVMe. We have about 60 terabytes raw storage, 20 usable with 3-factor replication. We have dual bonded 25 gigabit VLAN networks, fully fault tolerant, and we're using jumbo frames. For this setup, we have one Ceph pool for RBD with PGs of 8192. Our load generation environment is 10 nodes of R640 running RHEL Postgres 11.2. We set up 5 database server instances per node, giving us a total of 50. And that's essentially an untuned environment. So we did not, that's kind of a tricky thing to say, well, we have these database servers, but as you might know, tuning databases is kind of a whole world unto its own. And so really the thinking was, let's just kind of go with a default install. We'll adjust buffer cache, but we won't really get into tuning per se. We have 250 gigabytes RBD data volumes per database server instance. And we provision about 40% of our cluster. So we ended up using about 8 terabytes. We did a considerable amount of tuning of our cluster. So our approach was, when we started out, we set up our environment, we started running some baseline tests, and we started out using tests like FIO. And what we did is we captured a baseline set of tests and data without doing anything special, just kind of a sort of out of the box, more or less. And then we said, okay, now let's go through this methodically and systematically and come up with the very best performing cluster that we can come up with. So there are kind of 4 different categories of things that we looked at and things that we did. Of course, Ceph tuning is the first one that comes to mind. Finding the 8192 as the optimum placement groups was kind of a key thing from a Ceph tuning standpoint. As far as the other Ceph tuning parameters, we really relied pretty heavily on recently published Ceph tunings. And what we found is that what's currently published in recent publications is quite good. And so more or less that's what we use for our Ceph tunings. Similarly, for the OS tunings, we used essentially a lot of the recommendations and best practices from the recent publishings, and that worked out quite well. The third category that we looked at is our NUMA nodes or NUMA zones to find out, well, how are things currently configured in the server? Are they configured in an optimal way? And if not, what are some of the changes we can make to set it up in a more optimal way? So what we did is essentially 3 things. So the first thing is we have a pair of 25 gig NICs. So we separate those. Oh, and by the way, the first step of doing this is to have a really good understanding of your server. And you have to have a system diagram that tells you, for this particular server configuration that you have, how is it wired up so you can see the mappings of PCIe slots to whether that's on Proc 0 or Proc 1, right? So we had that in hand to start figuring out what goes where. So we separated out our 25 gig NICs. Then we took the NVMEs, as I mentioned, we have 4. So then initially we had all 4 on one proc. So we said, well, that's probably not the best way to do it. So we split it out. So we have 2 on each proc. And then lastly, the other thing is we essentially have two sets of non-NVMe storage devices. So one set is our HBA 330 JBOD OSDs, our SATA SSDs. The other one is our BOSS card, which is the RAID controller for the M.2 of the OS. So we split those as well. The fourth category of things that we looked at was actually some hardware changes itself. So initially we did testing with a P4500, and we changed that out to the P4600. We reduced the number of SSD drives. Initially we had 20. So the chassis that we're using is a 24 drive chassis, 2.5-inch drives, where we had 20 SATA SSDs and 4 NVMEs. And what we found is that, so this 20:4 is a 5:1 ratio. And we found that this ratio was not right because we ended up essentially overrunning the capacity of the NVMe. So as part of this tuning process, we removed 4 of the SATA SSDs, bring it back down to 16, and then that gave us a 4:1 ratio. Now we weren't overrunning the NVMEs. The other thing that we did was, initially we had H740p PERC controllers, and we changed that over to HBA 330 JBOD controllers. And the blue box on the lower right-hand side kind of gives you the big picture before and after. So before we did any changes at all on a particular, and this was a random read workload, before tuning we had 689,000 IOPS. Post-tuning, after all these changes have been made, we got up to right at 1.5 million IOPS for that particular set of load that we were running. So this is a gain of 116%. This was amazing to us. Because initially, when you start out thinking, well, okay, we start off with a baseline, don't really know what you're going to get until you start running some numbers. And then the idea of, well, how much do we reasonably expect to get out of these tunings? And I don't know, I guess maybe I was hoping, well, if we get 40%, that would be great. 50% would be really happy. But 116%, that's huge. So that's a big part, I think, of your Ceph deployments, your Ceph clusters, and if you have an environment where you really need that high performance, this is really an area that's worth looking into. So here's a quick chart to show you some of the PCIe slot assignments. And I don't want to go into this in any detail. It just shows pictorially what I described earlier. But really the idea is that it's balanced, mostly. That what you see on the left-hand side and the right-hand side is as close to a mirror as what we can make it. And this was very beneficial. Here are some of our benchmarks that we did. Again, this is before we're getting to the database workload. So this is just kind of the initial set of FIO benchmarks. And this is with our final tuned configuration. So for 4 KB random read using FIO with libRBD, this is the kind of performance. So on the left-hand side, you can see what our scaling is. And of course, as we increase the number of clients, latency, average latency goes up. On the right-hand side, you can see a graph that shows what our resource utilization is. On this particular workload, what we find is that once we get up to 30 to 40 clients, that we're really hitting the limits of what the disks can do. So that's the bottleneck in this case. Similarly, from the random write standpoint, same sort of idea. We did FIO benchmarks, libRBD, 4 KB random write, and this is what we got. Up to a little over 200,000 IOPS at 64 queue depth. But you can clearly see that the latency starts going up on you pretty quick. Similar thing here, we looked at the resource utilization, and as you can see from this chart here on the right, essentially at some point we hit the device limitations of how much load we can pump through it. Okay, so that was the baseline, getting us up to having something that's tuned, works well. We've done our initial tests. We're pretty happy with it. So now let's move on to the database part. So we use SysBench, which seems to be a really common tool, methodology for benchmarking the databases. We configured Postgres to run bare metal, as Tushar mentioned. We configured it with 25 gigabytes of shared buffers. We gave each instance a 250 gigabyte KRBD volume. And SysBench also was configured to run bare metal. So our prep step for SysBench, where we populate the data, we set up 32 tables per database instance, database server instance, with 14 million records per table. For every run, so we had 50 database server instances. Whenever we did the load test, each database server instance had its own SysBench proc that was generating load against it. Our approach was to have a 5-minute ramp or warm-up time, and then a 5-minute run time where we're collecting the data. In between each test invocation, we cleared caches on the Ceph nodes, so both the Linux caches as well as restarting the OSDs. We programmatically started, so we weren't, start with a keyboard interactively. Programmatically, we launched everything simultaneously to make sure that we have the concurrent load all running at the same time, where they're all in lockstep. So for our 100% read set of tests, this is the chart that shows our results, and you can see, so there are 3 things to take note of here. So on the left axis is our QPS, queries per second. And this number is the sum of all SysBench occurrences. So we have 56 SysBench processes running. This value on the left-hand axis is the sum of all 50. On the right-hand axis is our tail latency in milliseconds. And then along the x-axis is the number of threads that we run per SysBench. So just to make this very clear, so when I say 1, 2, 4, 8 threads, this is per SysBench. So if we're looking at it cluster-wide, it's these numbers times 50. For the write case, same exact idea. We have queries per second on the left-hand axis. We have tail latency on the right-hand axis, again in milliseconds, and threads on the x-axis. You can see how things go up, but you can also see how our tail latency goes up. So it's just really something you have to keep in mind about what are your latency requirements. So it really comes down to what do you need and what are you looking to get out of your system. Finally, we did a mixed workload test of 70-30, 70% read, 30% write. And again, we have a chart for that as well. Things work quite well, but as we would expect, tail latency also goes up as a function of our threads. Kind of taking that whole set of tests and methodology to say, well, what are some of the observations and recommendations that we have? What I'd say is Ceph is only getting better, and I've heard that in other talks as well. So if you look kind of at the evolution, we went from file store to BlueStore, Ceph Deploy to Ceph Ansible. Some of the monitoring has gone through several iterations. We can now run containerized, co-located daemons. But I think kind of the stepping back, the idea is if you start slow, you're deliberate about what you do, the crawl, walk, run, it's probably a pretty good way to go about doing things. I think it's a good idea to understand your drive failures. What happens in your Ceph cluster when you have drives fail on you? And what kind of impact is that going to have on your cluster performance? Kind of what you might say might be a little bit of a criticism. Ceph isn't fully a turnkey type of a product. So you should expect to be able to build out a few things according to your own environment. But I think one of the biggest things is that don't underestimate the importance of sizing and performance tuning, because it can make a huge difference. And based on the studies that we did here with this particular ready architecture, we believe that this particular all-flash cost-optimized configuration is a very good starting point for a general-purpose Ceph cluster. But again, it's a starting point, right? It's only a 4-node Ceph cluster. So with that, I'll turn it over to Tushar.
Let's check here. So this joint effort between Dell and Intel was to basically build out based on the hardware that's currently production, has been around for a while, and establish basically best practices and a small starting cluster configuration that's more of a recipe than a sizing, than what you would find in the sizing guide, right? So like Paul mentioned, we're also working together on a high performance all NVMe type of an architecture. So if you guys noticed in the charts that Paul was showing, the tail latencies are still in the hundreds of milliseconds range. Some of that is attributed to the HCI interface that's underlying, that's used with underlying SATA devices. There's actually more performance to be had with an all NVMe drive. So you'll see an all NVMe reference architecture that should come out soon. So I also wanted to cover, as we talked about a current technology, the Xeon Scalable processors that came out right about a year and a half ago at this point that were used in the reference architecture. The SSDs were P4600, which were also about 2 years old at this point. So what about the cutting edge, right? How do these numbers look like? What sort of improvements can you expect? So Intel released the second generation of the Scalable family on actually this month, April 2nd was the release. And a few of the things that were improved from the processes that were used as part of the reference architecture were basically additional higher core count, higher frequencies, at the same SKU price points. There were actually security mitigations built into hardware. So some of the performance that was originally lost to software workarounds, you could gain that back from this upgrade. And then there were several AVX512, AVX512 SIMD instruction improvements for your erasure coding or compression encryption sort of workloads, which will come handy as well. Along with this family of CPUs, Intel also tried to address the gaps in the memory and storage hierarchy. So if you look at traditional storage, the way the tiers, starting from the slowest tier possible, which is the hard drives or the tape tier, we had a jump in performance with NAND SSDs, which were in the last generation they were called TLC, which is tri-layer cell, where you're trying to pack essentially 3 bits per cell. And then at the top we basically had DRAM, which was, and if you look at the latency range, the DRAM is in 100 nanosecond range, the 3D NAND is in the 80 to 100 microsecond range, whereas the hard drives are in the millisecond range. So there was a big performance gap. So in the past year or two, we have done quite a bit of work to actually fill these gaps. So starting from the bottom, where at the lower cost performance balance, where we actually had a big gap there between in terms of latency. You actually had to spend quite a bit over hard drives to achieve that latency. So we introduced a new non-volatile memory technology called QLC, which is quad level cell, where instead of 3 bits per cell, you essentially are packing 4. And these devices are actually available in much higher densities than the QLC SSDs were. So these devices today are available up to 32 terabytes per device. So you can get to a much higher density per node for your Ceph or other storage applications. And then at the top, we also introduced Optane SSD, which improves the low queue depth storage performance, brings down the TLC latency from 100 microseconds down to 10 microseconds. So there's a 10x latency improvement. And talking about a little bit more in detail about the Optane technology. So your standard NAND SSDs actually work on pages or erase blocks. So for any update, you're going to cause a read modify write operation. And what that does is there's a negative impact on performance and latency as time passes. As the blocks get more and more blocks get full, the garbage collection takes a longer time, and the impact is on the latency. So the Optane media was actually developed as a brand new media. It's not a standard semiconductor NAND memory. It's actually a bit addressable device where all of the updates can be done in place, which means over time the latency impact is very low. So this chart shows how, for example, a NAND SSD, which is shown as the gray chart here, versus an Optane SSD behaves over time, which is this blue line. So if you look at, so the x-axis is time here, and the y-axis is essentially the write pressure. So as the write pressure increases, the NAND latency only gets worse, whereas the Optane latency basically stays flat, no matter what the write pressure or time. So why are we talking about Optane here? So in the context of Ceph, if you were concerned about your latency bounds being too wide, you could use Optane for Ceph BlueStore metadata, which is basically the WAL and DB partition could be put on a small Optane drive. There's actually a distinct cost performance benefit there, which we have some more slides in the backup, which we, and also available through some Intel blocks that you can refer to. But what this chart is trying to show is basically the left two charts, the top and the bottom chart, basically show when you have metadata co-located on a NAND SSD versus the right two charts where you're using Optane for metadata. As you can see, the latency band is actually much tighter, so which means your 99th percentile or 4/9 latency is going to be much better when you use Optane. So this is actually another thing that we'll introduce as part of the next generation arrays with Dell. So bringing all of these components together, right? The next generation Xeon CPUs, the QLC, and the next generation TLC SSDs and Optane. What does the solution look like? So I have a quick comparison between the previous generation CPU SSD technology versus the one that was just released. So I have two configurations. One is what we're calling a cost-optimized solution, where we are using the Cascade Lake, which is the newest generation Xeon CPUs, where you get more cores for the same cost. And the reason number of cores matter is, for those that are experienced with Ceph performance, would actually agree with me that the Ceph for Ceph performance, number of cores actually matters more than many other factors. It's a CPU-bound workload when you're talking about SATA or NVMe SSDs in the backend. So 2 additional cores actually do provide that 10% or 15% boost to performance. There's also base frequency increase. And the other thing we're doing in the next generation architecture is we are replacing the data drives with denser QLC SSDs, which are the 8 terabyte SSDs instead of the 4 terabyte. And we're also replacing the P4600 drives, which are the NAND SSDs, with Optanes. So as a whole, it actually gets you to a higher density at similar price point and better performance because of the Optane SSDs. The performance version of this solution would use not the QLC but the newest generation TLC SSDs paired with Optane. The rest of the recipe remains the same. So how does this look like in terms of performance? So if you compare the baseline, which is more like last year's baseline versus today, the cost optimized solution is about 70% better performance, generation over generation, whereas the performance solution, which is with the latest generation controllers on the TLC media as well as the Optane SSD, actually looks about 3.5x faster. So this is something definitely to look forward to. And for those that are interested in details around how does it do at individual block sizes, we do see a big benefit at the larger block sizes, up to 2.5x compared to the current baselines. Yeah, here are some more details on how it affects the latency. So we do have significant latency improvements. And one thing you will notice is that even the cost-optimized configuration actually provides pretty significant latency benefits, over its baseline config that we've been working on for the last couple of years. And that's mainly because of the Optane and the QLC combination that gives you that better latency performance. So we are back to the question. So are we there yet? So I'll let Paul give his take on it. So.
Thank you. So the question, are we there yet? I would say, in general, the answer is yes, we are, for the vast majority of use cases. There are some special cases that could be challenging. So if you have super tight latency requirements, or something really unusual about your environment that requires something kind of far out of the norm, then maybe not in some of those special cases. But as a general rule, yes, for sure, we are there. There's very good performance. There's a very solid foundation of Ceph that is quite stable, progressing, continually getting better. And there's a very vibrant community, so we only expect things to get better and better.
So for those highly demanding applications where let's just say you might complain about the 99th percentile latency that Ceph delivers today, which is in hundreds of milliseconds range. What are we doing to improve that? So at Intel, we have a commitment to open source, which includes Ceph. We actually have a 6-strong developer team that's working on Ceph. And here are a few features that are in the pipeline to address all the performance challenges, mainly on the latency side that we have, which are essentially we are introducing a client-side caching feature, which is recently merged. It should be complete within the next quarter or so. There's a crash-consistent write-back caching, which actually Lisa in the audience she's working on. We have a Crimson OST project. Crimson OST project was actually started last year after the community was convinced that they need to do something about the performance challenge. So this was an OST re-architecture exercise that was started, and it's going along pretty well. We have a single thread OST booting right now, and we have C* Messenger, which is basically an asynchronous messenger, higher performance than the current async messenger. That's in prototype. The nice thing about this work is most of this is already being merged to master. And for those end-to-end considerations, we're also working on block client performance improvements. For example, there are some limitations today with RBD with respect to op threads per RBD volume. There are actually some locking. The way the locking is done, it's too macro. We're trying to improve those places as well. So yeah, it's overall like Paul called out. It's only getting better. So we're almost at the end of time. Can we take a couple of questions, or are there any questions? Yeah.
So in your benchmark, why didn't you leverage RDMA for next for your Ceph?
So the question is, why did we not leverage RDMA, or did we? Yeah. So the answer is this was basically with the current state of the technology. So the Xio messenger has been in the Ceph tree for about 2 to 3 years now, but it's not officially supported as part of the Red Hat Ceph storage or SUSE. So this was actually mainly to leverage what's out there as a production worthy supported configuration. So yeah.
You said that the bottlenecks were at the drive layer. Was that the SAS interface to the drive or the drive itself?
The drives itself.
Yeah, and that's actually a great sign, right? That even 16 SATA SSDs, Ceph is able to saturate that. And I mean, in that sense, Ceph is already there. Yeah. Okay. All right, so we are out of time, but thanks a lot for attending, and yeah, appreciate it.